So this one is upward a long ways, but it's a small amount of mass. This one's downward, but it's more mass. So if you just multiply that by the mass, you can sort of think of these as the same. Because this one has more distance, but this one has more mass. So it's kind of, they affect the center of mass symmetrically. So the idea is that the center of mass, even after the explosion, continues to do what would have been done anyway. The center of mass just moves in a straight line, but the parts can fly off from each other. So you can kind of think of explosions in that way. So in that case, you'll have a situation where for the explosions, you will have a before and after. So you'll have two pieces stuck together before the explosion, and they share the same mass. I'm sorry, they share the same speed. They move together. So if one of them is moving 2 meters per second to the right, they both are because they're connected. So there's only one velocity. You could even write that as where you sort of put them together with parentheses. Oops. And they both get multiplied by the same v. If you distribute that v in, they both have the same velocity. But then after they blow apart, they now have their own velocities. So here you would take the two masses, multiply them by the common velocity, and you get a total momentum. If they're not moving, then you have a zero momentum, which is fine. And then after the explosion, let's say they did have a zero momentum. They were just sitting still, and then they blew up. Well, that means the whole system will still have zero momentum, zero motion after the explosion. You just have to realize that the parts cancel each other out. So one part might be moving with this momentum to this way, then the other part's going to have the same momentum moving in the opposite way, so that if you added them up, they would add to zero. So that's one thing. If the two things were moving together like a rocket and then it blows up in the air, the parts, let's say sort of like a little rocket sort of like breaks into a cloud and it's on the moon, like it's a tiny little toy rocket. It disintegrates into a little cloud of dust, and let's say there's no air resistance, there's no air, and you can sort of, it's just gravity. The rocket would normally maybe follow a trajectory like this. But when it explodes, pieces fly off, and it ends up where when they hit the ground, if you calculated their center of mass, it would still be right where the rocket was going to land anyway. So the pieces might move away from the center of mass, but an explosion would have no effect on the system as a whole. It's really just one part of the system pushing on another part of the system, and through Newton's third law, where equal and opposite reactions, there's no effect from an external perspective of the system. So we could do a problem like that. Let's say you've got something standing still, so it has zero velocity. Let's say you've got a 4 kilogram mass and a 10, and they're not moving, and then they explode. The 10 kilogram mass, you now know, is moving to the right at 5 meters per second. So what would the 4 kilogram mass be moving with what velocity? Well, before, the total system momentum was 0. So that means altogether, you've got to have 0 total system momentum after the explosion. If this thing has a mass of 10 and a velocity of 5, that means it has a momentum of 50 to the right, which means altogether, this thing has to have a total momentum of 50 to the left. So I know 50, rather than negative 50, is going to have to equal that 4 times, well, times an unknown velocity, 1 after the fact. So you just got to divide by 4. And the new velocity will be 12 and a half to the left meters per second. So it works just the same. There's just different types of situations. Sometimes they're stuck together and then they blow apart. Sometimes they're apart and they come and stick together. Sometimes they don't stick together. Sometimes they bounce. You always have a before and after, and you're just taking m times v for this and m times v for that, finding the total system momentum. That's got to be conserved. That's got to stay the same before and after. And then you just got to make sure that the m times v after for everything adds up to be the total that you had before. Hopefully that's not too complicated. You guys okay with that so far? Any questions? Okay. Good. So that is momentum. It's important. One, it's conserved. It's a conserved quantity. It's a little problematic because it doesn't seem to tell you everything. You kind of need to be given one piece of information about how something is moving after, and then you can find the other piece. It doesn't really tell you what both things will do if you didn't know either of them. Energy could help you with that. One thing that they found with energy, though, was that energy seemed to leak. It seemed to leak out of the system. So if you push somebody on a swing, you give them energy, and over time it sort of puckers out. Or if things collide, sometimes they maintain their energy. They have the same energy before and after, but there were some situations where they wouldn't retain their energy. So momentum was looking stronger for a while, but it had some drawbacks. What they ultimately discovered was energy is much deeper than people realized. Another thing that they studied completely separately from motion was heat. And nobody really knew what it was. Why are things hot? Why are things cold? What's going on there? Well, we've now unified those theories. So heat is now explained in terms of motion, of atomic and molecular sized structures. And we've now learned that the systems that do seem to lose energy isn't getting destroyed, it's transforming into other forms. And it's actually, like if I take a brick and I slide it across the table, it will stop. It'll lose that energy, but the energy left the brick. It hasn't disappeared. It's now heating up the brick and heating up the wood. And the guy Joule was the guy who first quantified. He was a brewer. He brewed like beer, and at the time that controlling the temperatures of things and precisely as brewers had to was beyond experimental physics at that time. Like they were like the best in the world at controlling temperatures. So he was a brewer who brought his craft sort of into physics, and he was able to create tanks with like paddle wheels inside them with water, and he put spindles where they would, string would be tied to the paddle, and he'd put hanging weights on them, kind of like, I'll try to draw it. Like you had like sort of tank, you had like a paddle system. You know what? I'm just going to look it up on Wikipedia. How about that? Instead of trying to draw it. There we go. Sure. So he had some sort of little system in this tank with a thermometer, obviously, and he could take a weight and drop it, causing a certain amount of mechanical energy. We haven't talked about calculating that yet, but he could calculate how much energy he put into the system. That would stir the water, and he would just keep dropping weights over and over again until he was able to figure out a conversion between a calorie is like 1 degree change of water and a unit of mechanical energy. So he was able to say, okay, when I lose this much mechanical energy, I'm changing this body of water. And if I do that enough, I can raise it 1 degree. So they came up with what they called the mechanical equivalent of heat, which is like the motion equivalent of heat. And they were able to show that heat is energy. Like the energy is not lost. It doesn't die. It transforms. So very interesting. So that's why the unit of energy is the joule. It comes from that guy. He's sort of restored the notion of energy because he showed, oh no, energy doesn't leak. It's not worse than momentum. It's conserved too. And it's actually more interesting because the energy can actually change forms from one form to another. We'll get more into energy later, though. We'll just stick with momentum for now. But momentum and energy kind of came into the picture at the same time, like collisions and explosions. That's sort of where we first started working with them. So this is how you sort of do these conservation of momentum problems. It's really just, this. And the formula for momentum is this. And there's a couple examples of how you solve these problems. Yeah, it's always just a before and an after. I think that's pretty good. I don't want to go into energy yet. And there's more we can do with momentum, but I just want to do one thing today. If that seems okay, then that's all I really need to go over with you, I think. There is another worksheet that can be due in a week, Wednesday. And so you can ask questions on Monday. And it should be like what I just went over. Does that sound okay? Any other questions then? All right. Well, I know, Colin, you had a question. So I'll let everyone else go if you're good then. If you didn't have a question on the other assignment, then you are free to enjoy the rest of your day. Have a good one.